Hi and welcome to this new lesson of this R video tutorial. In this lesson I will show you how to perform an ordinary Kriging interpolation on your data using R and the package gstat. On the home page of the course you can find the dataset that I'm going to use for showing how to perform the Kriging. I just put it on this folder. So it basically is the same data and the same shape and ASCII grid that I used in the previous lesson. So there is this data, which is a table with latitude, longitude, and the property of interest. I add a column ID to identify each row, and then there is a shapefile with a polyline of the border of the area, and the organic matter ASCII grid, which is a raster. Put the script that I'm gonna use for this lesson. So we can start by opening R, and for this lesson we are gonna use the package gstat. So you need to install first. So go to install packages, select the crown mirror close to your location, scroll down to reach the letter G, and install the package gstat. So it's gstat. Okay. Now it's downloading it and installing the package. So now we can load the R commander. So scroll down and click R commander and OK. And then we can open the script that I create for the last. So you can go on desktop, because I put the script on the desktop. So in this case I select script and OK. And this is your script. In the first 4 lines are comments, so I just put a title to the script too. The other 4 lines, as I show you in the previous lesson, are to load the necessary packages that you'll need for this lesson. So because I have to import various type of spatial data, I need the package rgdal for importing the shape file, the map tools package for importing the ASCII grid, the gstat and the sp package for the interpolation. So I can just select the 4 line and submit them. And now it's finished loading it. I can set the working directory. So in this case I just go to my desktop, copy the link, return to R commander and just paste the link here. As I show you in the previous lesson, you have to double the backslash in order to for R to recognize the address, submit, and here is now your working directory is on desktop for lesson. So all the data that you need now are on that folder, and you can avoid writing the entire address of the folder. Just write the name of the data. So with this line I can read the table data.txt that I showed you before. I can view a little summary of the data. As I showed you before, there is another column ID which identifies each line with a number. Now I can transform with this line my data into a spatial object data frame, and if I repeat the summary, you can see that now it's not a data frame anymore like before, but it's a spatial point data frame. Now I can give it to it a coordinate system. In this case it's UTM-33. So I can just use this number which identify the UTM system zone 33 north. So if I just repeat the summary, you can see here that he has recognized the coordinate system. Here there is the address where you can find all the coordinate system IDs. Now, as I showed you in the previous lesson, I can use the function read OGR to read the shapefile. So I can just read it and then give it to in the same coordinate system. In this case, as you can see here, it's a spatial polygon data frame because, as I said, this shapefile is a polyline. So now I can use the function read AsciiGrid to import the ASCII file and give it the coordinate system, the same one. And if I want to see how this object looks like, I can just use the function str, which is a summary, put the name of the object, close the round bracket, and submit. As you can see here, there is said that it's a spatial grid data frame because it's a raster. Of course, as I showed you in the previous lesson, you can take a look at your dataset using the function spplot, which is a plot function for the SP package. I show all the options available in this function in the previous lesson, so here I can just submit the line and show you this image with the raster and with a plus symbol of your observation. Of course, the main purpose of an interpolation is to predict the property of interest in all the other locations that you did not sample. So in all these other locations over here within your area of study. So the first thing to do is create a prediction grid for your interpolation. In order to create a prediction grid, you can use the following line. You can just take the following line and pass it to your script because they are a default code. I also borrowed it from the internet, so you can do it. You can borrow your code for whatever you want. The only line that you want to change is this one. That give you the grid size of your grid. In my case, I used 5 meters, but you can use, of course, other resolution. So I can just submit the entire the entire part of the script for creating a prediction grid. And as you can see here, the last option is to write the prediction grid as an ASCII grid in the file predictiongrid.asc. So I can just submit the entire block, and if I take a look at my folder, as you can see here, it has created a predictiongrid.asc. This is important because I will use it at the end of the interpolation to predict the property of interest in all these other points. To show you how the grid looks like, I can just use the function plot and no NAs, which is the final name of the grid. And it's very simple grid. Of course, this is my area of interest, and this is the simple grid. Now we can proceed to the important bit of this lesson, and the first thing is the variogram. How to create a variogram and how to fit a model to it. So the first thing is a plot to show you how the variogram looks like. The function for creates a variogram is very simple. It's variogram. You can use a formula to give the variogram the linear model. In this case, because it's an ordinary Kriging, the linear model is the variable of interest, and it's just a variable of interest. So in this case, it's oxygen 1, and this is your dataset. So you can just take a look at the variogram and all the parameters. So in this case, because it's an horizontal, it's a omnidirectional variogram, so I don't have a direction, but I have a number of pairs, distance, and gamma. So now I can just use the function plot, submit the variogram, and here is your variogram. This is the semivariance and the distance. In order to fit a variogram model to your variogram, you can use the function vgm, which create a model for your variogram. So I can use I can set the seal of your variogram, the model, in this case a spherical, the range, and the nugget. I'm using the setting that I took from spatialanalyst.net. So I'm using the variability of the property for the seal, spherical model, because as you can see here, apparently the spherical model is the best fitter, so you can use it. The range is the square root of the area of the raster divided by 4, and the nugget is 0. So I can just submit this line and proceed. Of course, as I said, you can go to the site spatialanalyst.net, which is a very good site, and you can find a tutorial, not in the video form, but it's still a very, very good tutorial for regression Kriging, and it will show you all this function, how to create a variogram, etc. So now I can, because I create a variogram object, I have to fit this object to the variogram. In order to fit the variogram model to the real variogram, I can use several functions. There is the Remel function, the ordinary least square, and the generalized least square. As a rule of thumb, the generalized least square is very slow, and in my experience, it doesn't work with a large data set, because of course there is a problem with R about the memory that it can use. So with in the normal 32-bit machine, the generalized least square minimization algorithm is very difficult to use. So I usually use the Remel if it's appropriate, or if it's not, I can use the ordinary least square minimization algorithm. So now, in this case, I will show you how to use both. So the first fitter is the Remel algorithm. So the function is fit.variogram.remel. I use the same formula. The data object, in my case, is data, and I have to give the function the model of the variogram. In this case, is mod that I just created. So I can just submit this line, and here you can see that he has created the variogram model. In order to plot the variogram model, I can just use the same function that I used before. So plot variogram and the model, and with the title, of course, Remel model. So I can just submit this line, and as you can see here, there is the variogram with the attached model. Same thing with the ordinary least square algorithm. The only difference is that is not a function, but is the general function fit variogram with the option fit method 6, and 6 stands for ordinary least square. So this function, I can just use the variogram, the omnidirectional variogram, the model, and of course the fitter function. So you can just submit and use the same type of plot, of course, with this object that I just created, which is stands for the model with the ordinary least square. So I can just submit, and here you can see there is a little difference in the model. Usually to see which one is the best, I usually prefer to go with the one-out cross-validation and just see which model perform better. So here is the function that you can use for the one-out cross-validation, which is Krig.cv, and just give it the formula, the linear model, the data, and the model, which is in this case is not the variogram model that you create with the VGM function here, but is the model of the variogram that you already fitted. So in this case, I want to use the fit REML. So I can just submit this line and perform the cross-validation, the one-out cross-validation. So in this case, basically it takes one observation out of your dataset and repredict the same point with all the other observation. To see what is the goodness of fit of this observation, I prepare for you a couple of standard index, the Pearson R-square and the root mean square deviation. You can just submit this line and create this object, but because I want to show you what is the value, I can just submit just the line and without creating the object. So in this case, the R square is 0.16 and the root mean square deviation is 3.32. So now I can use the same exact method, but with the ordinary least square model. So submit this line, perform the cross-validation using the ordinary least square model. It should take a couple of minutes, not much, because the dataset is not huge. So now it has done it. Calculate the R square. In the previous case was 0.16. In this case is basically the same. Maybe it's a little higher. The root mean square deviation, maybe it's a little higher as well. So in this case, both models are equal. You can, in this case, you can choose whatever model you like for the interpolation. If you want, you can also plot the predicted value with the cross-validation and the observed value with the 45-degree line with the function AB line slope 1 and intercept 0. In this case, I want to color red, so I can just submit these two lines. And as you can see here, because the R square and the root mean square deviation is not high, the observed and predicted value, they are not close to the 45-degree line. In this case, the prediction is very pure. But I'm hoping that with your data it will be much better. Now I can show you how to perform an independent validation, because in the previous case it was a cross-validation. A cross-validation basically it's the program takes one value or more than one value out of your observation dataset and repredict it. You can also, with this function Kriging, you can also perform a n-fold cross-validation. If you want to see how to do it, you can just type help Krig.cv, submit this line. It will open the help page of the function, and here you can see that there is the n-fold option, because the default option is n-fold 1, so it performs a one-out cross-validation, but of course you can use the function n-fold and type, I don't know, 4 to perform a 4-fold cross-validation. The problem is that if you have a very large dataset, this type of cross-validation, it takes very long time. So if you want to try an independent validation, you can also create two subsets of your data, a training subset and a test subset, with a different percentage of observation in the test dataset, and then using your training dataset to predict your test dataset and compare observed and predicted value in the test dataset. So now I will show you how to create these two subsets with a 10% validation point, and how to perform the comparison. So the first thing to do is select the number of rows that I want to use for the training data and the number of rows in my dataset that I want to use for the test data. In order to do that, I want to use the function sample. The function sample basically select randomly from a set of data a certain number of or percentage of observation. So in order to show you how it works, I can just use an example. So I will give you a range 1 to 100. So my original set is a number that goes from 1 to 100 by 1, because in this case I use the column symbol. So the original set is this one, as you can see here. And from this dataset I want to take randomly, just say 10 observation. If I submit this line, as you can see here, it's taken 10 observation randomly from the dataset that I gave it to him. In this case, I have 200 rows in my dataset. nRow is the function to display the number of rows in this dataset. I want to select 10% of these rows, so I can just use this simple formula to say that the 10% of 200 is 20. But of course, I want to select randomly 20 cases from this set. So I can use the function sample with 200 as my original set and 20 as the number of observations that I want him to exclude. Click submit, and as you can see here, he has selected randomly, completely randomly, 20 observations. So I can just submit the object, create the object I, and then use the object with this selection method, because of course, as I show you in the first lesson, in order to select a certain row from a dataset, I can just use this formula within square bracket and with a comma, because I don't want to select line but just rows. So in this case, I want to use all the object in the column data ID which are not equal to I, because of course I is 20, so training must be all the other that are different from the 20 that I want to select. So in this case I can use this symbol to say that I want to exclude I from my data, and because I create the column ID with the number of row, I can use it to say that I want all the other rows that are not equal to the value that are within the vector E. So I can just create this, and I can show you how it looks like. It's a data frame, and I can also create a test, and to show you how it looks like, I can just click submit, and as you can see here, there's the 20 observation with coordinates and variable of interest. So now I can just use the function Krig, which is the main function for Kriging. I can give him the dataset, which in this case is not data anymore, but is training, the model that I want to use. In this case, because I saw that maybe it's a little better, I can use fit with the ordinary least square. And as a new data to perform the prediction, instead of performing in the entire dataset, I can just perform it in the test dataset because it's an independent validation. So I can just click submit. It said here that it has used ordinary Kriging, and then I can calculate the goodness of fit like in the case of the cross-validation. So I can just R-square is 0.25 and RMSD is 2.1. Of course, in this case, the result looks much better, but in the reality is that maybe they are very similar to the previous case, because of course in this case he has selected 20 points from 200, and maybe the random selection was particularly good for the prediction. So in this case, if you want to if you do not have a very large dataset, because of course if you have a huge dataset you cannot repeat the same independent validation many times, but if you have a smaller dataset that you want to use this type of validation, maybe it's better to perform it several times and calculate the mean of the goodness of fit indexes. Of course, you can also plot, as I showed you before, the observed and predicted value with the 45-degree line. So I can just use observed values, which in this case are text oxygen, and Krig var, because var1 pred, because the object Krigs, which is this one, the object Krig look like this. If I show you, I can just print Krig. In this case, there are 20 observations, and there is coordinates, var1 pred, which is the prediction that he made, and the error associated to each prediction. So I can just submit these two lines, and as you can see here, there is the result. Finally, if you want to predict, because now you know which model for variogram is the best, you know the value of the cross-validation, so now the last thing to do is create the final map with the prediction. So you can use the function again Krig, the same formula, the entire dataset, the model, because I saw that it was best, so I want to use the ordinary least square, and the new data in this case are the grid that I created at the beginning of my script. So you can just submit this line, and then when you see this blue line using ordinary Krig, it means that he has ended this prediction. So you can just use the function spplot with the map, which is the object of the map, the variable that you want to show, which in this case is the predicted values, and the color scale that you want to use. Submit, and here is your prediction with your color scale. If you want to plot the variance associated to the prediction, so instead of using var1 point pred, you can use var1 point var, because I said instead of using terrain color, you can use heat map, so heat colors, and submit the line, and here is the error associated to your map. Okay, so this is the end of this lesson about ordinary Kriging. In the next lesson, I will show you how to perform a universal Kriging with your data. See you next time.